everyone for complying with our time constraints. We were able to get back on schedule, which is very nice. So I'll try to keep it short as well, so we are even more on track. Okay, so today I'm gonna talk about how to combine a problem called goal recognition. Most of you are familiar with it, and MARL. Sorry. Okay. So first of all, so we've talked about RL today, even before the multi-agent part. We can cite this diagram in our sleep. And often the problem that we solve here is we have an agent environment and we are improving an MDP policy. And when we say improving a policy, we mean that we usually want to maximize the reward that we get in some execution. But often what we care about in many of the talks that we've seen today is not actually maximizing reward, is reaching a goal, to reach some point, some state that we want to accomplish, or having something that we didn't have earlier. And this is a crucial difference. And when we talk about multi-agents, agents have incentives, they have goals. Usually what we talk about are goals. When we talk about our L, usually what we talk about rewards. And now we have this gap that we need to bridge. How do we translate goals into rewards? What is the connection between the entity goal, the entity that is an agent, and the entity that is an MDP, an RL problem, the reward function that we have? So potentially there are many different relationships that you can combine these all together. I've been to the goal conditioned RL workshop at New York this year. They had 31 papers that try to solve this problem in different contexts and try to suggest different solutions. And most of them were trying to take an RL problem and optimize it, assuming that what the agent is trying to do is reach some goal. And they try to reach some end goal in mazes. They try to do manipulation tasks. They try to play games. 3 of them had real world examples that I appreciated that. One was medical decision support system, explanation selection, and parcel routing that were more grounded in real life. But still, it brings up this same illustration that we are all familiar with. We identify a problem, we construct a data set, we train a model in RL, we evaluate it, and then we publish. We found a good policy. But what this policy really is, what were we actually able to accomplish? Are we able to navigate with autonomous vehicles? Are we able to perform robot manipulation? As Sarah mentioned, picking up something is hard. We can play simulations in Joko, we can play Minecraft. So I want to argue in this quick talk that RL, in multi-agent RL, is our means. It's not the end goal, if you got the pun here. We do care more about the goal. And if you think about autonomous vehicles, we care about other agents, we care about are they trying to bypass, are they trying to change lanes? When we talk about service robots, we want to understand what our customers want so we can help them. With Da Vinci robots, operation, shared control, we need to understand what are the intentions of the operator, of the physician. For adversarial purposes, we need to understand not just how an attacker intends to attack us, not just that. We don't just need to understand that someone wants to attack us, we want to understand how. This is the point in intercepting an attack. And even if we think about a jam session with a robot, we would like to have a jam session with a robot, it needs to understand what are the next steps that we wish to play so it can create a harmony. So what's connected to all these multi-agent settings is that these are all examples that require theory of mind. We need to somehow understand the goal of other agents in our environment. So as a problem, goal recognition has a long and respectable history. In 1986, it was formalized as the problem of inferring the goal. Originally, it's a plan, but I'm gonna simplify it here for a goal of the agent given observations in a database of recipes. So if I see my husband in the kitchen breaking some eggs, melting chocolate, and I know that he only makes recipes from a specific recipe book, I can infer that he's gonna make us a chocolate vodka. So this is the classical goal recognition formulation. Traditionally, it was solved using planning approaches or other symbolic approaches. For example, what goal recognition is planning does, plan recognition is planning, it represents a domain theory, which is a great world, what we can go, where we can go, what we can do, and a set of observations. And the task is, given these, understand what is the likely goal of the agent. Here, between 1, 2, and 3, which goal is most likely? 2. As people, this is so easy for us. For agents that use symbolic approaches like planning, you need to have a PDDL of the environment to understand what does that mean, where you can transition, and then what plan recognition is planning does, you take 2 plans per goal, one that reaches the goal, one that does not. And you try to compare which one is more likely and the cost between the different plans. And then you infer, because these observations match plans that match goal 2 more, that it is the most likely goal. But this is a long and cumbersome process, and you need to formalize that, like Ronnie mentioned in his talk, you need to have this model prepared. So that's the key issue with previous work on goal recognition. In the real world, we have some raw data, and we need to first take an activity recognizer to just process that, to get these symbols that we can work with. And we also need a domain theory. This is PDDL, hand-coded. Now, after we have this and we have that, and that's a lot of human effort to construct, we get some observation, we use a plan or a parser, and we infer that this person is making breakfast. And there are several challenges to use this approach. First of all, the cost of domain description. So this is a PDDL, and this is cumbersome to encode. But if you think that this is challenging, try write CCGs, combinatorial categorical grammars. They're fantastic. They are so robust to represent stuff, but you don't really want to compile that yourself. They're very susceptible to noise because you basically give here the description of what ought to be happening. It's not what happens if we bias from that. And the real world is very, very noisy. So it's very easy to shift from that, and it's very hard to incorporate noisy trajectories and understand things with this representation. And because we need to run planners online, it is very costly. So recently, I proposed together with Leonardo Amado and Felipe Meneguzzi a new approach where we take the domain theory and we basically replace it with a set of policies of Q functions in the cell. You can look at it as Q functions as policies. We have a Q function or a policy for a goal. Now, what we do here, basically, we've learned that an agent that tries to reach goal A will behave this way. When we have an agent that tries to reach goal 2, they will behave that way. Now we have different distributions of how agents can react. We no longer need to have a planner. We just need to take an observation sequence and a policy and compare whether this observation sequence is reasonable given this policy or not. And then we can infer whether a person is making breakfast or not. So the first phase in this approach is learning. We replace the domain theory, the coded domain theory, with a set of MDP-based policies. And later, we just need to infer whether the observation sequence and the policies match or not. So just to give you an example, I'm not going to go into the details of the approach here because this is not the point of this talk, but just to give you an example of how we do that. Again, we have the same candidate goals and observations as before. Now what we do in the preliminary phase, we learn the domain instead of encoding the domain. And this is a policy that we imagine an agent pursuing goal 1 will take. This is the policy for an agent pursuing goal 2, and this is for goal 3. And once we have this, once we get the observation sequence, we can infer that this is a match. This is a behavior that we expect an agent to take. This one. All of the red ones are the ones that match the observations. So you can see that for goal 1, none of the observations match. So this is probably not the right policy, not the right goal. This has only 1 and this has 3. Now this is a running example. It's very simple. Of course, in real life, you want to have probabilities because here, this is an optimal action, but also going right is optimal. I'm making it look simpler here. The important part is that once I have these policies, it's much easier to compare them to get an inferred goal. So in our paper, and this is what I'm going to skip in this talk, but please, this is a line of work that I'm pursuing now, actively pursuing and extending. So if you find this interesting, please come to me offline. I'll be happy to talk about it more. We propose the first step in that, goal recognition as Q learning, where the learning phase, we use tabular Q learning. And in the second phase, we proposed using different metrics, max util, which just aggregates the utility of the in a trajectory we observe, KL divergence and divergence point, different ways to estimate whether an observation sequence and the policies that we learn, which goal is the most likely one. So again, going to the experimental setup, we had 3 different domains that we used: box rule, Hamoy, and estate read. And we compared 3 variations of Grackle, the algorithm we developed, and we gave 500 training episodes per policy. Now, what's 500 in reinforcement learning, in multi-agent reinforcement learning? That's ridiculous. That's like, we've only started. This is something you can run on your CPU. That's no fun here. But this is the exciting part about this work. In goal recognition as reinforcement learning, policy learning is not the end goal. I don't really care about having a perfect policy for goal A, a perfect policy for goal B. I only care about the policy for goal A and goal B to be different enough that when I observe an agent in the environment, I can understand, okay, this agent is going to pursue goal 1. So my problem is much, much easier than optimization here. And I can cheat in many different ways because I don't really care about the optimization task. Since I can do this, after 500 training episodes, I can already run my algorithm, and we compared it to the classical plan recognition as planning algorithm that I mentioned earlier. We had overall 210 goal recognition problems with varying observability levels and noise levels. Just because we need to see some graph. This is the F score of whether each algorithm was able to find the right goal given a sequence of observations. And you can see here max-util KL and DP the Gretel versions, and this is the classical traditional goal recognition as planning. And you can see that in all domains except for DP, both KL and max-util were very, very good. And this is for full observability. Once we have partial observability, once we have noise, you can see a significant decrease in the performance of the classical algorithm, while the other algorithms maintain very good performance for very complex problems. So this was a huge win, and this was just the first try of taking an RL algorithm to solve this problem. And going back to the classical goal recognition and augmenting it with RM. So we were able to reduce the cost of domain description because we are now learning them instead of coding them ourselves. We are much more robust to noise because we are not looking at a PDDL, but on a policy. So it covers, if we have a full policy, then we do cover the whole state space. So it's much easier. And no online costs because we don't need to run planners anymore. Now we just need to compare a metric, whether an observation sequence and the policy match or not. So this was really great. Sorry, this is about a different work that I'm not going to talk about. So the point that I wanted to make in this talk, and the reason I've mentioned this work specifically today, is because I think, first of all, when we talk about multi-agent RL, we need to identify what are the entities we talk about. We talk about RL, we talk about agents, we talk about policies. How do they connect to one another in your work? We briefly mentioned cooperative, mixed incentives, adversarial, but what do we really mean by that? Do they have mixed goals? Do they have mixed beliefs about the environment? What exactly is aligned between different agents and what is not? What is the role of each agent in our setting? These are things that we usually take for granted when we have a specific setup, but if you actively try to think about it, I argue that you can gain much more knowledge, maybe assumptions you can leverage. Once you know, for example, in my domain, I do goal recognition, so I don't need to optimize policies, which gives me a lot of availability and flexibility in terms of the RL algorithms I'm going to use. And later on, how can we extend these relations? If we are working on a specific setup, how we can extend that to a new setup, given that now I am full aware of the use of the RL agents and policies in my work. So thank you for listening, and I'll be happy to take your questions.
So I'm really not going to optimize policy, but can you optimize for recognition?
For recognition?
Yeah, so optimize your QLM for recognition. So you learn partner different, something like inspired by what you
So that's a great question. Currently, we are learning policies using RL agents where their goal is to optimize for that. It would be interesting to have a perspective where the reward that we shape for them is try to reach that goal, because we assume that this is what you get. It would be interesting to tell them, try to reach that goal in a way that is different from the other goals, like having this force model. That would be very interesting, yeah. No? Yes.
I thought maybe about the opposite idea. Maybe the goal are not so different. The goal is the same. You want to reach something, but the method is different in its policy. But you want, if you merge the goals, but you split them to different policies, but the goal itself is the same.
That's fantastic. That's the core difference between goal recognition and plan recognition. In plan recognition, we care about the how you reach a goal. So that's an interesting question, whether we can take goal recognition as reinforcement learning and make that a plan recognition problem. We haven't thought of that, but that's a very valid way to extend this work.